California grows about 80% of all strawberries that are produced in the United States, making them a very valuable asset to California's economics. In 2017, strawberries were the fourth most valuable crop produced in the state behind dairy products, grapes, and almonds, bringing in about $3.1 billion. The California Strawberry Commission is a company that represents more than 400 strawberry processors, growers, and shippers throughout California. They are a state government agency that is focused on conducting research to support California's strawberry industry. The research department in San Luis Obispo proposed optimizing and commercializing the current vacuum. The Lygus bug is a pest that eats the seeds on the strawberries, which causes deformation, resulting in $100 to $200 million worth of damage every year.
The Lygus bug vacuum consists of a hydraulic motor attached to a fan that is housed inside the ducting unit and is attached to the front of a tractor. A grate is attached to the top of the ducting unit, which the bugs hit at a high speed and are killed. As the tractor drives over the strawberry field, the vacuum creates a suction force that sucks up the Lygus bug. This is the current design that the California Strawberry Commission designed and uses. There are several different designs, all homemade due to the lack of commercialization. The California Strawberry Commission was requiring our group to design a Lygus bug vacuum that can be commercialized, increase the kill rate of Lygus bugs in one pass over the field from 20 to 30% to 40 to 50%, decrease the noise emitted by the current system, and stay within a $1,500 material budget. Our design constraints were that the system has to cover the typical 48-inch strawberry bed, it must fit on the front of a tractor, the tractor power is limited to 110 to 120 horsepower through the PTO, it must be lightweight in design in order to reduce compaction and increase mobility, and it must be aesthetically appealing.
After the field trip to Guadalupe, the team decided that the tooth vacuum supported by a plexiglass box was a more realistic design to strive for than the CNN. The requirements that we decided that would be most beneficial for increased airflow were no necking and using a smooth material. Some other considerations that we determined might be helpful for improving the design were installing 1 or 2 fans per duct to increase the airflow, angling fans on the bottom of the ducting to blow at the plants to disturb the bugs, insulation to reduce the vibrations and noise of the system overall, industrial rubber flaps on the sides and the back of the box to prevent Lygus from escaping, and soft bristles on the front to disturb the Lygus enough to break them free of the strawberries but not harm the plants or spread diseases.
The testing unit was built from disassembling the initial prototype. The goal of making this was to be able to swap out the ducting size and test the effect of the gap between the end of the fan and the duct on the airflow. This was the most important principle in designing the ducting, so it was justified that we spent the first 3 weeks making this unit. We also wanted it to be tall in order to test how the distance away from the inlet of the ducting affected the wind speed. The system had to be movable with a forklift to ensure that it could be moved in and out of Shop 6. The wind speed test consisted of testing the effect of wind speed when using different sized ducts. A 24-inch fan was tested with a 26-inch and 30-inch duct. We used this velocity map created by the fan optimization team to keep track of the 600 data points. We tested how wind speed changed when moving further from the inlet by taking measurements at the inlet, 3 inches, 6 inches, and 12 inches below the inlet. We ran each test 3 times and used an anemometer to collect the wind data. From this testing, we learned that the measurements at the inlet towards the edge of the ducting had the highest wind speeds. We also saw a 30% increase in the wind speed from the 30-inch to the 26-inch ducting at the inlet, meaning that the gap between the wingtip and the duct made a big difference, and as a result, we knew that we needed to make the duct only slightly bigger than the fan.
The noise test consisted of measuring the noise of the testing unit under 4 conditions: without insulation, with just interior insulation, with just the exterior insulation, and with both the interior and exterior insulations. We collected information on how distance away from system affected noise. We also measured vibrations with an accelerometer. From these tests, we learned that there are a lot of vibrations at every location on the ducting, so to prevent this, it would be best to make the ducting out of fiberglass. We also learned that the system is very loud, 110.2 decibels, and we need more ear protection than just earplugs. The noise was about the same, however, regardless of insulation, the further away from the ducting. The best thing to combat the noise for the operator would be to add both insulations on the final product.
To make the frame, we built the 6 foot by 3 foot rectangle out of the aluminum T-slotted framing provided by the California Strawberry Commission to save on costs. To make the ducting, we cut a 4 foot by 8 foot piece of 16 gauge sheet metal into a 30-inch by 61.25-inch rectangle and rolled that into a 19.5-inch cylinders. We then MIG welded the sheet metal together and grinded down the welds to have a smooth, clean surface. We assembled the metal frame for each duct and bolted the ducts to each frame. The ducts were then mounted to the aluminum frame using some custom rods that the fan optimization team made.
For the final product, we created 3 cylinders that were 19.5 inches in diameter and mounted them in a triangular shape to cover a standard 48-inch strawberry bed. It was mounted inside the 6 foot by 3 foot aluminum frame. We added additional support beams to prevent the frame from bending and cut holes in the ducting for the fan mounts and hydraulic lines. Some things that we learned while making this final product was that the process of rolling metal took longer than expected. Our inexperience in welding and grinding created thin spots and some holes in the metal. The ducts did not end up being perfectly circular, which made it hard to fit in the fans. And the project was bottlenecked because the process of fabricating each duct took longer than expected.
Overall, the final project ended up working very well. The California Strawberry Commission was pleased with the research we did and the final product we created. Some things that we learned from this project is to plan on everything taking longer than expected, outsource some of the more challenging tasks, ask for assistance and other references, and constantly confirm data collection and design specs with your sponsor. We would like to thank John Lynn from the California Strawberry Commission who made this project possible, and Dr. Haberlin and Dr. Bates for helping us along the way.